Ladies and gentlemen, focus is not just a mental concept. It is a dynamic neurobiological process governed by specific systems within the brain. At its core, focus is the ability to direct cognitive resources toward a particular task while suppressing irrelevant information. This ability hinges on a tightly coordinated relationship between the prefrontal cortex, the thalamus, and various neuromodulators that regulate arousal alertness. The prefrontal cortex plays a central role in executive functions, the higher order processes that allow us to plan, reason, and concentrate. When we focus on a task, this region becomes highly active, sending signals to other parts of the brain to prioritize certain sensory and ignore others. The thalamus acts as a gatekeeper for incoming sensory information, deciding which inputs are worthy of attention and which should be filtered out. These two structures work in concert to determine what enters our conscious awareness and what is pushed aside. This process of gating and prioritizing information is not static. It is heavily influenced by neuromodulators, chemical messengers that fine-tune brain activity. One of the most important neuromodulators involved in focus is norepinephrine. Released primarily from the locus coeruleus, a small nucleus in the brainstem, norepinephrine heightens alertness and primes the brain for detecting and responding to stimuli. Its release increases during states of attention, making neurons in the cortex more responsive to relevant inputs. However, too much norepinephrine, often associated with stress or overstimulation, can impair focus by inducing anxiety and hypervigilance. Optimal levels of this neurotransmitter support a balanced state of alert concentration. Another critical player is acetylcholine, which enhances the brain signal-to-noise ratio. This neurotransmitter helps sharpen the representation of relevant stimuli while suppressing background noise. Acetylcholine's release is tightly linked to attentional effort and task engagement. It acts like a highlighter in the brain, emphasizing what matters and fading what doesn't. Dopamine, commonly associated with motivation and reward, also influences focus by reinforcing the relevance of specific tasks and maintaining engagement over time. The brain does not operate in a vacuum. It constantly interacts with the environment, and sensory inputs, especially auditory ones, can significantly affect focus. In today's digital world, many people struggle with sustained attention due to an overabundance of stimuli. Phones vibrate, notifications ping, conversations murmur in the background, each pulling cognitive resources away from the task at hand. This sensory overload taxes the attentional system and forces the brain into a mode of continuous switching. Each switch depletes neuromodulatory reserves and leads to mental fatigue. Noise in this context becomes a critical factor. Not all noise is detrimental. Certain types of noise, specifically consistent, low-frequency sounds, can actually help the brain maintain a focused state. This is where the scientific understanding of auditory masking and neural entrainment becomes relevant. By introducing predictable, non-invasive sound patterns into the auditory environment, the brain can downregulate the distracting effects of unpredictable background noise. The thalamus is less likely to pass on irrelevant information when the auditory environment is stable and non-disruptive. The concept of noise as a tool for attention enhancement might seem counterintuitive, but it rests on solid neurophysiological principles. The human brain evolved in natural environments filled with rhythmic, low-frequency sounds, wind rustling through trees, rain falling steadily, or waves lapping against the shore. These sounds are not just aesthetically pleasing, they create an ambient auditory scaffold that supports calm alertness. From a neurological perspective, such sounds can reduce activation in the default mode network, the set of brain regions associated with mind wandering and internal distraction, and enhance task-positive networks that drive goal-directed behavior. Understanding how focus operates in the brain and how it is affected by external noise opens up avenues for practical interventions. While pharmacological methods exist to modulate attention, such as stimulants that increase dopamine and norepinephrine levels, non-pharmacological tools like sound design offer a safe, scalable alternative. This leads into the exploration of how specific types of noise, like brown noise, can be harnessed to support the brain's natural attentional mechanisms without chemical intervention or overstimulation. Brown noise, also known as Brownian noise or red noise, is a type of sound signal characterized by a particular spectral density. In technical terms, it is a signal with a power density that decreases by approximately 6 decibels per octave as the frequency increases. This means that lower frequencies are significantly more prominent than higher frequencies, producing a sound that is deep, rich, and rumbling, reminiscent of heavy rainfall, distant thunder, or the deep hum of an ocean wave. The name brown noise is somewhat misleading. It has nothing to do with the color brown. The term comes from Brownian motion, named after the botanist Robert Brown, who observed the random movement of particles in fluid. Brownian motion refers to a random walk process, and brown noise is generated by integrating white noise, which is equal intensity at different frequencies over time, resulting in a sound whose power accumulates more in the low frequency range. This process creates a signal with a spectral profile that is smoother and heavier at the bottom end of the frequency spectrum than white or pink noise. To understand how brown noise functions at a physical level, it's helpful to consider the differences between white, pink, and brown noise. White noise has equal intensity at all frequencies, leading to a bright static-like sound. Pink noise, often compared to the sound of rainfall or wind, has equal energy per octave and is slightly more balanced across the frequency range. Brown noise, by contrast, significantly emphasizes lower frequencies, producing a much deeper and fuller sound. The energy in brown noise drops off steeply as frequency increases, which gives it a characteristically soothing, non-intrusive auditory profile. From a signal processing perspective, brown noise is generated by passing white noise through an integrator circuit or performing a cumulative sum across its values. This cumulative summation means that the waveform of brown noise changes more slowly and gently than white noise, leading to less abrupt variation in amplitude over time. This makes it feel less harsh and more grounded to the human ear, while white noise contains high frequency content that can be perceived as sharp or hissing. Brown noise has much less of that high-end content, making it feel more muffled and enveloping. The human auditory system is particularly sensitive to different frequencies in different ways. Brown noise, due to its low frequency dominance, interacts with the auditory system in a way that can have calming and stabilizing effects. Low frequency sounds tend to be processed by both the cochlea and neural pathways in the auditory cortex in a manner that can influence physiological states. This interaction has implications for the use of brown noise in various therapeutic or functional contexts, including focus, sleep enhancement, and anxiety reduction. One reason brown noise is thought to be effective in supporting attention and relaxation is due to its ability to mask external sound distractions. In noisy environments, the brain is constantly shifting attention in response to auditory intrusions, conversations, keyboard taps, cars passing outside. Brown noise, because of its continuous and low frequency profile, can act as an auditory blanket, suppressing the brain's response to sudden changes in ambient sound. This effect, known as auditory masking, is most effective when the masking noise occupies similar frequency bands to the distracting sounds. Brown noise's deep, rumbly spectrum is particularly well suited to masking lower frequency intrusions such as distant voices or environmental hums. Additionally, exposure to consistent low-frequency sounds like those in brown noise has been associated with shifts in brainwave activity. While the data in this area are still emerging, some studies suggest that such auditory stimuli can promote alpha and theta brainwave state of sensory containment. For individuals with sensory processing sensitivities or attention difficulties, this cocooning auditory experience may help regulate arousal levels and promote deeper focus on internal or task-related stimuli. Brown noise interacts with the brain through multiple neurophysiological and perceptual pathways, influencing cognitive processes such as attention, sensory gating, emotional regulation, and arousal modulation. Its low frequency, high energy nature makes it particularly effective at shaping how the brain processes auditory information and maintains focus in the presence of environmental stimuli. Understanding how brown noise influences brain activity requires exploring its effects on both the sensory processing systems and the large-scale neural networks involved in cognition. When brown noise enters the auditory system, it is first processed by the cochlea in the inner ear. The cochlea performs a frequency decomposition of the sound, separating it into distinct frequency bands that are transmitted via the auditory nerve to the brainstem and onward to the auditory cortex. The auditory cortex, located in the temporal lobe, interprets these signals to construct our perceptual experience of sound. Because brown noise contains more power in the lower frequency ranges, typically below 500 Hz, it primarily stimulates the apical regions of the cochlea, which are more responsive to low frequency sounds. These frequencies are not only processed differently than higher frequencies, but are also less likely to produce fatigue or overstimulation in the auditory system, allowing for prolonged exposure without discomfort. The consistent and smooth nature of brown noise has a direct impact on the thalamus, which acts as a relay and filter for sensory information entering the cortex. The thalamus plays a central role in attentional control by determining which sensory signals are prioritized and which are suppressed. In environments filled with unpredictable intermittent noise such as a busy office, a city street, or even a digital workspace, the thalamus is frequently triggered to pass along novel auditory signals to the cortex, which in turn distracts the individual from a task. Brown noise, because of its predictability and lack of sudden changes, generates a steady auditory input that requires minimal cognitive attention. This allows the thalamus to downregulate its filtering activity, reducing the frequency of interruptions in conscious thought and enabling more consistent engagement with the task at hand. On a larger scale, the brain operates through networks of coordinated activity. One of the key networks involved in focused attention is the frontoparietal control network, which connects the prefrontal cortex with the parietal lobes. This network supports executive functions like decision-making, working memory, and sustained concentration. In contrast, the default mode network, DIM, becomes active when the brain is at rest or engaged in self-referential thought, such as daydreaming or internal narrative. The interplay between these two systems is a constant push and pull. When the frontoparietal network is active, the DIM is usually suppressed, and vice versa. Brown noise has been shown through both anecdotal reports and preliminary neuroimaging data to support the activation of the task-positive networks like the frontoparietal system by reducing internal and external distractions. This supports a cognitive state conducive to deep work, or what is sometimes referred to as flow. At the level of brain waves, brown noise may also facilitate shifts in the brain's electrical rhythms. The human brain cycles through different frequencies of electrical activity depending on the state of consciousness and cognitive engagement. For example, beta waves 13 to 30 Hz are associated with active thinking and problem solving, while alpha waves 8 to 12 Hz correspond to relaxed yet alert states. Theta waves 4 to 7 Hz are typically linked to meditative, introspective, or drowsy states. Brown noise's low-frequency structure may entrain or encourage brainwave patterns associated with calm focus, particularly in the alpha range. While more rigorous scientific studies are needed to fully establish this connection, EEG studies have shown that certain types of rhythmic auditory stimulation can modulate cortical rhythms and promote desirable mental states for focus or relaxation. The brain also responds to brown noise through its regulation of the autonomic nervous system, particularly in modulating levels of physiological arousal. The autonomic nervous system is responsible for maintaining internal balance, including heart rate, respiration, and stress hormone release. The consistent, low-frequency input of brown noise may contribute to a parasympathetic shift activating the branch of the nervous system associated with rest and recovery. This parasympathetic dominance can reduce the release of cortisol and other stress hormones, decrease heart rate variability in a positive way, and promote a state of calm alertness. This is especially important for individuals who experience heightened stress response in noisy or unpredictable environments, as brown noise can create a stabilizing auditory and cognitively, the brain prefers predictable sensory input when engaged in tasks requiring sustained attention. Random or disruptive stimuli demand frequent updates and processing, which deplete cognitive resources and increase the likelihood of task switching. Brown noise, by offering an unchanging and low-complexity input, reduces the brain's need to monitor and adapt to the auditory environment. This decrease in vigilance frees up cognitive capacity to engage more deeply with goal-oriented tasks, whether reading, coding, writing, or meditating. In this way, brown noise functions almost like a cognitive buffer, preserving attentional energy and protecting the mind from the fatigue associated with overstimulation and distraction. The neurological mechanisms involved in how brown noise affects focus and concentration are rooted in the dynamic interplay between auditory processing systems, attention regulating circuits, and neuromodulatory pathways. Brown noise, by virtue of its consistent low-frequency output, interacts with specific components of the central nervous system in a way that alters sensory input processing, modulates cortical excitability, and influences the chemical milieu that governs mental states such as alertness, calm, and sustained attention. At the core of auditory perception lies the cochlea, a fluid-filled structure in the inner ear that converts sound waves into neural signals. Brown noise, which consists of frequencies predominantly in the lower spectrum below 500 Hz, stimulates the apical end of the cochlea where low-frequency sound waves are registered. Once these signals are transduced, they travel via the auditory nerve to the cochlear nuclei in the brainstem, and from there ascend to the inferior colliculus, the medial geniculate nucleus of the thalamus, and ultimately to the primary auditory cortex and the temporal lobe. These ascending pathways are not purely linear. They include multiple feedback loops and inhibitory circuits that allow the brain to prioritize, modulate, and contextualize incoming auditory data. The constant and unchanging pattern of brown noise reduces the likelihood of abrupt changes in this auditory input, allowing the brain to settle into a steady processing rhythm without being repeatedly interrupted by novel or jarring stimuli. One of the central structures involved in focus is the prefrontal cortex, particularly the dorsolateral prefrontal cortex, BLPSC, which is critical for executive function, working memory, and goal-directed behavior. This region maintains attention by actively inhibiting irrelevant sensory input and enhancing the salience of task-related signals. When the brain is exposed to an auditory environment filled with variability and unpredictability, the DELPS is forced to repeatedly reallocate attentional resources. Brown noise mitigates this reallocation by creating a stable auditory backdrop, which the brain quickly categorizes as non-threatening and non-essential, thus allowing the DELPS to stay engaged with the primary task. In addition to the prefrontal cortex, the thalamus plays a crucial gating role in attention. It serves as the brain's central relay station, filtering sensory information before it reaches conscious awareness. The reticular nucleus of the thalamus in particular is involved in controlling what sensory information gets passed on to the cortex and what is inhibited. With continuous exposure to brown noise, the thalamus adapts by decreasing its response to that specific auditory input, effectively reducing the flow of unnecessary auditory signals to the cortex. This attenuation of irrelevant noise signals supports a more focused cognitive state by preserving cortical bandwidth for processing task-relevant stimuli. Another mechanism through which brown noise exerts its influence is via the brain's neuromodulatory systems. Norepinephrine, primarily released from the locus coeruleus, is a key neuromodulator involved in vigilance and arousal. In states of stress or high stimulation, norepinephrine levels rise sharply, heightening sensory sensitivity but also increasing distractibility. Brown noise, due to its non-threatening and repetitive structure, does not activate the locus coeruleus in the same way that erratic noise or sudden auditory events do. Instead, it can contribute to a more balanced release of norepinephrine, maintaining alertness without triggering hypervigilance. Acetylcholine, another vital neuromodulator, plays a direct role in enhancing the brain's signal-to-noise ratio. It does this by increasing the strength of relevant neural signals while contributes to what many users describe as a calming, grounding effect of brown noise, a subjective experience that likely reflects a real or chemical shift toward lower cortical arousal levels. On a network level, brown noise helps maintain activity in the task-positive networks, such as the frontoparietal attention network, while suppressing the default mode network, DIM, which is typically active during mind-wandering and self-referential thought. By reducing sensory variability and supporting a consistent sensory environment, brown noise decreases the activation of the DIM and prevents the brain from drifting into introspective or unrelated thought patterns. This supports the maintenance of an externally directed attentional state, allowing for deeper and more effective engagement in cognitive work or study. The sensory integration of brown noise does not operate in isolation but in concert with other modalities, including visual attention and motor coordination. Cross-modal attention is a well-established phenomenon in neuroscience, and auditory cues, especially those that are rhythmic or constant, can help stabilize attention across sensory domains. In this way, brown noise provides a kind of sensory anchor, reinforcing stability not just in the auditory domain but across the broader attentional landscape of the brain. The application of brown noise for enhanced concentration involves leveraging its unique auditory properties to stabilize cognitive performance and reduce attentional drift in environments that are typically filled with distractions. Whether in academic settings, professional workspaces, or therapeutic environments, brown noise serves as a tool to mediate. The sensory integration of brown noise does not operate in isolation but in concert with other modalities, including visual attention and motor coordination. Cross-modal attention is a well-established phenomenon in neuroscience, and auditory cues, especially those that are rhythmic or constant, can help stabilize attention across sensory domains. In this way, brown noise provides a kind of sensory anchor, reinforcing stability not just in the auditory domain but across the broader attentional landscape of the brain. The application of brown noise for enhanced concentration involves leveraging its unique auditory properties to stabilize cognitive performance and reduce attentional drift in environments that are typically filled with distractions. Whether in academic settings, professional workspaces, or therapeutic environments, brown noise serves as a tool to mediate work. It becomes a major liability. These frequent, often unnecessary, reorientations of attention come at a cost. Each one interrupts task-focused neural circuits and demands that the brain expend effort to reestablish the original cognitive context. Brown noise counters this problem by filling the auditory environment with a stable, predictable soundscape that prevents these orienting responses from being activated. The sound lacks variation, surprise, or salient auditory markers, and therefore it does not demand attention. Instead, it masks or neutralizes other background noises that would otherwise trigger a shift in focus. The brain, upon registering this constant low-frequency signal, quickly habituates to it. Once habituated, cognitive systems are less likely to be interrupted by unexpected sounds. This auditory consistency allows higher-order brain regions, particularly the prefrontal cortex, to maintain persistent activation patterns associated with goal-directed behavior, working memory, and attentional control. The utility of brown noise is not limited to masking disruptive stimuli. It also functions at a neurophysiological level to regulate arousal, a critical component of concentration. Arousal in this context refers to the level of neural and physiological alertness. Too little arousal results in drowsiness and inattention, while too much arousal creates anxiety and hypervigilance, both of which are detrimental to sustained focus. Brown noise can help maintain optimal arousal by gently stimulating the auditory system without overloading it. Its low-frequency characteristics may contribute to parasympathetic nervous system activation, promoting a state of calm attentiveness that is conducive to cognitive performance. This balance supports a mental state where the brain is alert yet relaxed, fully engaged but not overwhelmed. Students and knowledge workers alike have found that brown noise can extend the length of time they can remain engaged in cognitively demanding tasks. In study sessions, for example, brown noise creates an auditory boundary around the learner, buffering against incidental classroom or household noise. The effect is a subjective feeling of being insulated from external distractions, allowing deeper immersion into reading, problem solving, or conceptual integration. For those engaged in creative work, writing, designing, coding, the immersive effect of brown noise can reinforce the flow state, a condition of peak cognitive efficiency characterized by full involvement and diminished awareness of time. The application of brown noise also extends into clinical and neurodivergent contexts. Individuals with attention deficit hyperactivity disorder, ADHD, sensory processing disorder, or generalized anxiety disorder often struggle with environmental noise sensitivity or rapid shifts in attention. For them, the steady, grounding presence of brown noise can serve as a therapeutic intervention, helping to smooth out peaks and valleys in neural arousal and reduce the frequency of attention lapses. In ADHD, where deficits in dopaminergic and noradrenergic signaling underlie difficulties with task persistence, brown noise provides a non-pharmacological way to structure the sensory environment and improve task engagement. Within digital interfaces, the integration of brown noise into productivity apps and focus platforms has become increasingly common. Whether through browser extensions, mobile applications, or ambient sound playlists, users can easily incorporate brown noise into their work routines. These implementations often allow customization of frequency range and amplitude to better suit individual preferences, which is key as different brains respond differently to specific auditory textures. Some platforms even combine brown noise with visual focus tools or time management strategies, such as the Pomodoro technique, enhancing the effectiveness of each method by creating a multimodal support system for concentration. Workplaces are also beginning to adopt sound design principles based on findings from auditory neuroscience, integrating brown noise or similar low-frequency backgrounds into shared spaces to foster focused collaboration and reduce cognitive fatigue. In open office layouts where acoustic privacy is often compromised, installing sound masking systems that include brown noise has been shown to improve task performance and reduce stress. This kind of auditory architecture aims to create an environment where the default state is one of cognitive stability, minimizing the sensory unpredictability that undermines deep work. In more personalized applications, brown noise can be paired with noise-canceling headphones to create an individualized cognitive bubble in crowded or noisy environments. This approach is particularly effective during commutes, in public spaces, or in homes where control over the auditory environment is limited. The portable nature of brown noise through digital devices makes it an accessible intervention for anyone seeking to regain control over their attentional bandwidth. By providing a consistent auditory foundation, brown noise helps individuals regulate their cognitive engagement, maintain continuity of thought, and reduce the mental friction associated with environmental unpredictability. The effectiveness of brown noise in enhancing concentration and cognitive stability is deeply influenced by individual differences and contextual variables. While the underlying auditory and neurological mechanisms are consistent across humans to some extent, the subjective experience of brown noise and the benefits derived from it are shaped by personal preferences, neurophysiological profiles, environmental factors, and the specific nature of the cognitive task being performed. As such, personalization and context are critical components in determining how and when brown noise should be applied for maximum benefit. Individual auditory perception varies significantly. Some individuals are more sensitive to low-frequency sounds, while others may find them soothing or grounding. This variability stems from both genetic predispositions and experiential factors, such as early exposure to noise, environments, auditory training, or even trauma associated with sound. For example, someone with a heightened auditory startle reflex may find certain frequencies of brown noise to be calming, whereas others might experience discomfort or fatigue from prolonged exposure. This points to the importance of tailoring the sound profile, adjusting frequency bands, volume, and duration to fit the unique sensory tolerances of the user. Some people may prefer deeper, rumbling tones closer to the lower end of the brown noise spectrum, while others might gravitate towards slightly higher frequencies that still retain the smooth, non-invasive quality of brown noise but align better with their personal auditory threshold. Neurological diversity further shapes how individuals respond to brown noise. People with attention deficit hyperactivity disorder, ADHD, autism spectrum disorder, ASD, or generalized anxiety disorder, GAD, often experience atypical sensory processing and cognitive arousal patterns. For someone with ADHD, brown noise can serve as a sensory anchor, reducing external distractions and helping to regulate internal fluctuations in attention. However, the same auditory input might have different effects depending on the momentary state of arousal or the type of task being performed. A task that requires intense analytical thinking may benefit from a slightly louder or more dominant brown noise setting, while creative tasks or meditation might require a subtler background layer. In the case of individuals with ASD who may be hypersensitive to sound, the personalization of volume and tonal quality becomes even more crucial. Fine-tuning the noise to match comfort levels can mean the difference between a tool that facilitates focus and one that causes sensory overload. The context in which brown noise is used also plays a decisive role in its effectiveness. A quiet home office presents a very different auditory environment than a bustling cafe or an open-plan workspace. In a relatively silent room, even a moderate volume of brown noise might be unnecessary or could introduce unneeded stimulation. Conversely, in a noisy setting filled with erratic or human-generated sounds, a stronger brown noise signal might be necessary to adequately mask distractions and create a perceived sense of auditory consistency. Additionally, the type of cognitive load being managed matters. Tasks that involve rote memory, reading comprehension, or technical execution may benefit from one kind of brown noise setting, while abstract thinking, brainstorming, or deep strategic planning might require another. There's also a temporal aspect to consider. The brain's sensitivity to sensory input shifts throughout the day based on circadian rhythms, fatigue, and hormonal fluctuations. Morning cognitive sessions might benefit from a different brown noise configuration than late-night work periods. Early in the day, when cortisol levels are naturally elevated and alertness is higher, users might prefer a gentler auditory backdrop. As mental fatigue sets in later in the day, a more enveloping and immersive brown noise signal could help maintain cognitive stability and reduce susceptibility to environmental disturbances. This suggests that even within the same user, optimal brown noise settings are not static. They must evolve to match changing internal and external states. Technological delivery methods also shape how personalization is achieved. Mobile applications, streaming platforms, and dedicated sound machines often include sliders or presets for adjusting tone, layering brown noise with other ambient sounds like rainfall or ocean waves, and timing exposure through session-based designs. These tools can empower users to experiment with combinations until they find a personalized profile that supports their focus, mood, and task requirements. Additionally, wearable devices that monitor physiological indicators such as heart rate variability, skin conductance, or brainwave activity are increasingly being integrated with adaptive sound environments, allowing brown noise to shift dynamically in response to real-time changes in cognitive state. This approach turns passive listening into an interactive, responsive tool for cognitive enhancement. Furthermore, cultural background and language exposure can influence how individuals interpret and react to sound environments. Some cultures are more tolerant of environmental noise, while others emphasize quiet and stillness during periods of focus. A person who grew up in a densely populated urban area may find brown noise reminiscent of familiar soothing background rumble, while someone from a rural or quieter background might perceive the same sound as intrusive. These cultural associations can affect the emotional response to brown noise, shaping how readily it can be integrated into daily routines or cognitive practices. Past experiences, positive or negative, with similar sounds also play a role, as does the intention behind listening. A user who actively chooses to use brown noise for a specific task is more likely to perceive a benefit due to the alignment of conscious intention with environmental control, which enhances perceived agency and focus. Ultimately, personalization is not a one-time adjustment, but an ongoing process of tuning the sensory environment to match the user's evolving needs. Factors such as task complexity, emotional state, time of day, and individual neurobiology must all be considered when applying brown noise for enhanced concentration. The context, physical, psychological, and situational interacts with these personal elements, determining not only how brown noise is received by the brain, but how it integrates into the broader cognitive ecosystem, supporting focused thought and mental clarity. Establishing practical protocols for using brown noise effectively begins with understanding the dynamics of attention, environmental control, and physiological arousal. Brown noise is not a one-size-fits-all intervention. It is a sensory tool that requires thoughtful integration into daily habits, work routines, and focus-intensive tasks. The goal is to strategically apply brown noise in ways that enhance mental stability, reduce distraction, and maintain optimal cognitive engagement throughout various contexts. To do this, one must consider variables such as timing, duration, task type, equipment, environmental compatibility, and personal responsiveness. One foundational aspect of practical usage involves the timing of brown noise exposure. Many individuals find that initiating a session with brown noise at the very start of a task sets the attentional tone and creates a psychological boundary between preparation and execution. By beginning with brown noise, the auditory system is immediately engaged with a stable, non-distracting input that suppresses competing sensory inputs. This front-loading of auditory stability allows the brain to slip more easily into a task-focused state, particularly when paired with a consistent work cue such as sitting in a dedicated workspace or opening a specific application used only during focused work. The brain rapidly forms associations between the presence of brown noise and a shift into productive cognitive mode, reinforcing the neural patterning of focused engagement over time. The duration of exposure is also a key variable. Some users benefit from continuous exposure for extended periods, especially during deep work or monotonous tasks that demand steady concentration without interruption. However, others may find that extended listening leads to auditory fatigue or diminishing returns. For these individuals, cyclical protocols are often more effective. For example, pairing brown noise with structured time management methods, such as the Pomodoro technique, allows users to listen for 25 to 50-minute blocks, followed by a silent or nature sound-based break. This pattern not only optimizes cognitive energy, but also prevents over-reliance on any one sensory input. It also mimics natural rhythms and attention, allowing the brain to oscillate between periods of concentrated effort and low stimulation recovery. Another important factor in developing an effective protocol is the type of task being performed. Different cognitive demands may benefit from slight alterations in the sound profile, such as the intensity, pitch, or layering of the brown noise. Analytical tasks such as data analysis, coding, or studying technical material may require deeper, more immersive sound that fully masks peripheral noise and reduces environmental unpredictability. Creative tasks such as writing, sketching, or brainstorming may benefit from a subtler brown noise profile that provides sensory grounding without impeding internal ideation processes. Even repetitive tasks such as administrative work, filing, or organizing digital content can be optimized with brown noise, as it can reduce cognitive fatigue by minimizing the attentional toggling caused by background disruptions. The quality and delivery of brown noise matter greatly in practical application. Listening through high-fidelity headphones ensures that the low-frequency elements of brown noise are fully rendered without distortion, which is essential for achieving the calming and masking effects. Over-the-ear headphones with active noise cancellation can further enhance this effect by reducing the intrusion of ambient sound. In more stationary environments, such as home offices or therapy rooms, high-quality speakers placed strategically in the space can provide a fuller, more enveloping sound field. The key is ensuring consistency in volume and tone, avoiding peaks or dips that could trigger unnecessary auditory attention or interfere with habituation. Many sound platforms allow for loop playback with seamless transitions to maintain the illusion of an uninterrupted acoustic environment, which helps sustain cognitive flow. Device-based personalization is another pillar of practical protocol development. Whether using a desktop app, a mobile device, or a dedicated sound machine, users should experiment with settings that fine-tune brown noise to match their environment and preferences. Adjustable frequency curves, volume control, timer settings, and the option to blend brown noise with other ambient elements such as soft rainfall or wind can help users identify a profile that supports their specific task demands and mood state. Tracking subjective performance metrics such as perceived productivity, distraction level, and mental fatigue before and after brown noise sessions can provide feedback for refining protocols over time. Some users also find value in journaling or using digital tools to log their experiences with different settings and durations, contributing to a personalized optimization loop that becomes more accurate with use. In group settings or shared environments, implementing brown noise protocols requires sensitivity to others' preferences and needs. For example, in an office setting, providing personal sound options through individual headphones rather than room-wide speakers allows each user to control their experience without affecting others. In educational environments, brown noise may be made available through individual tablets or study booths, ensuring that its benefits are offered without disrupting group cohesion or learning dynamics. When applied in therapeutic contexts, such as with clients who experience sensory overload or attentional difficulties, brown noise can be introduced gradually and with close observation, ensuring that it enhances comfort rather than introducing additional sensory input stress. For optimal effectiveness, brown noise should be incorporated into broader attention regulation practices. This may include aligning its use with physical cues such as posture and breath, behavioral techniques such as mindfulness or cognitive reframing, and cognitive tools like task batching and mental rehearsal. When these practices are synchronized, brown noise acts as an amplifier of internal focus mechanisms, not just as a background feature. In other words, it becomes a component of a larger ecosystem of cognitive self-regulation, one that is adaptable, user-specific, and optimized for both neural efficiency and psychological comfort.